The relativistic Doppler effect is important in its own right, but we are ultimately going to apply it to understand the twin paradox. But let's start general and note that the Doppler effect refers to a situation in which you have a source sending out a signal toward an observer and there is relative motion between them, right? This is something that you have experienced, no doubt, with sound waves, right? The ambulance is coming rushing by, and the siren, right, you hear it, it goes, right? You've heard that? That's because the sound waves are piling up as the vehicle is coming toward you, making the frequency higher. As it rushes away, the sound waves are stretched further and further apart, so the sound goes down. That basic idea that you have experienced is something that applies to light as well. And since light is something that travels fast at the speed of light, you need to take relativistic effects into account to mathematically understand what is happening. So let's take a look at that and do a calculation. So what we're going to try to figure out is if you have light that, say, has a frequency nu, and if you have an observer that is moving relative to that light with a velocity v, our goal is to understand the frequency that the observer will see relative to the frequency at which the light was emitted. And let me give you the answer before we derive it. That is the formula that we are going to find. The frequency observed can be gotten from the frequency at which the light was emitted by multiplying by this factor. Square root of 1 minus v over c divided by square root of 1 plus v over c. Just a little calculation to establish that, so let's take a look. Alrighty, so let's imagine that we have a source over here, and that source is sending out some light waves. So let's draw a few of those. So the light waves are all emanating from the source, something like that. And imagine that you are receiving that light. So let's say imagine you are right over here. But let's also imagine, let's do the case where, say, you are running away. So you are moving away at a velocity equal to v. And we want to figure out the frequency with which you receive those light waves. Now, a couple little details worth emphasizing on the side. Remember quite generally from your understanding of waves that the wavelength of light times its frequency, that is the speed of light. So this is equal to c. And therefore, it'll be useful for us to write this in the form nu is equal to c divided by lambda. And lambda, of course, if we want to draw it in the picture, is the distance between these wave crests. So let's imagine that one of these wave crests has just hit you. You're moving away. You want to know how long it will take for the next crest to hit you. How long will it take this one to reach you? That's not hard to do, because if you call that time delta t, it had better be the case that the speed of light times delta t is equal to the distance it needs to travel. Now, at first sight, you might think that distance is lambda, but now that we've done this kind of calculation many times, you recognize that you were moving, so actually you've moved over here. So the distance between your initial and your next location there is going to be v delta t. So the light has to cover that distance as well for this next crest to hit you. And therefore, we can solve for delta t. Delta t, bring that over to the other side, is just lambda over c minus v. Now, we're not quite done, because this delta t over here is the time that we, watching this unfold, would say took place. The time, according to the observer, him or herself, is delta t prime. That watch, of course, is ticking off time slowly. So we need to take delta t for us and multiply by a number less than 1. Of course, it's either going to be gamma or 1 over gamma. Don't get confused about them. Don't even try to figure it out from a formal mathematical sense. You need a number less than 1, since this time is less than this time, and that therefore means it must be 1 minus v squared over c squared. So now we can plug in for delta t, and we will have what we are looking for. So writing this, say, as lambda over c times 1 minus v over c, that's the same as that expression, that's delta t, times the square root of 1 minus v squared over c squared. I'm going to play a game here. This can be written as 1 plus v over c times 1 minus v over c. So let's write that. 1 minus v over c times 1 plus v over c. And then I can bring this guy inside by squaring it. One factor will cancel against that, leaving us with 1 plus v over c over 1 minus v over c and the square root. So we have lambda over c square root of 1 plus v over c divided by 1 minus v over c. Now that's the amount of time it will take for that next crest to hit. If we're interested in the frequency, so the frequency observed, of course, that goes like 1 over the time between when the crest hit. Bigger frequency means less time between each of these hits, and therefore we need to flip that guy upside down, c over lambda square root of 1 minus v over c, 1 plus v over c. And then we recognize from the formula that we have over here that that is just the frequency at which the light was emitted, this term in front. So this is nu emitted times square root of 1 minus v over c divided by 1 plus v over c. And indeed, that is the formula that we advertised, giving us the frequency observed in terms of the frequency emitted, a factor of square root of 1 minus v over c divided by square root of 1 plus v over c. And you can play with a nice little demonstration that I will leave it to you to manipulate, where you can choose the velocity of the source, you can choose the wavelength of the light that it's emitting, and you'll be able to see how the frequency of the light changes depending upon whether the source is coming toward you. That would be if you were in this location, or if the source is moving away. As you will note, if the source is coming toward you, the frequency will go up, which means that the color of the light will shift toward the blue. That's blue shift. If the source is moving away from you, the frequency will go down, because that means that v would be positive in that case, and that means the light gets shifted toward the red. So that's the essential idea of the relativistic Doppler shift. Let's then go on to understand how we would apply this idea not to light in general, as we've described here, but to the case of interest that we will apply this to in a moment, when we have our two characters, George and Gracie, sending flashes to one another, because it's just a moment's more work to recognize that the formula that we have derived here will be just as relevant in that case. What do I mean by that? Well, each flash that George and Gracie sends to the other, you can really think of each flash as just like a crest of a wave. So rather than thinking crest after crest after crest, you can think about it as flash after flash after flash. So exactly the same formula that we have derived for how the frequency of the wave changes can now be interpreted as how the rate of flashes changes based upon your relative motion. So there is the relativistic Doppler shift formula that we have derived for frequency. We now just reinterpret it as giving us the rate at which flashes are observed compared to the rate at which they are emitted. And I can show you a couple of visuals that will make that link between this picture and the flash picture a little bit more direct, or more precisely, between this formula and the formula that we are going to use in the case of flashes. So let's take a look at an example where we can see that interpretation in terms of flashes in action. So here, George is throwing one flash after another, and get a feel for the rhythm as Gracie receives them. So 5, 6, 7, 8, 9, right? You can feel that. But now let's change things and have some relative motion between them. In this case, Gracie's going to run toward the flashes, and look what happens as she does so. Get a feel for the rate at which she receives them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? You feel it. It's going faster because she's running toward them, and we would make use of our formula in which, as we've seen, the rate increase is augmented even more by time dilation, so that with v replaced by a minus v, which means that the rate at which she receives them goes up relative to the rate at which they were emitted. And you can look at the various other combinations too. So now we are going to do a case where Gracie, the source, is going to run. So George gets them 3, 4, 5, and so on. Now, if Gracie runs toward him, that also is a case where v would be negative as they are approaching each other, and get a feel for the rate at which George receives the flashes now. So she's still throwing them at the same rate, but he's going to get them 1, 2, 3, 4, 5 faster because of the relativistic Doppler effect. So that gives you a good sense of how the relativistic Doppler effect can be reinterpreted as giving us an understanding of the rate at which flashes are emitted versus how they are received. You should play around with a little demonstration over here where you can basically do a version of the animation that I just showed you. So here we have the velocity of a source, and I'm going to have the source throw out flashes in both directions. And you will note that the flashes on this side are piling up, so a person here would get them quickly. 1, 2, 3, 4, 5. Someone over here, very slowly. 1, 2, 3, 4, 5. So play around with that, because that's just an illustration of the relativistic Doppler shift formula. Our goal ultimately will be to apply this formula to the twin paradox, where the twins are sending signals back and forth. But the relativistic Doppler shift formula is vital and important in its own right. So look at the equation and try to get a feel for the math by manipulating the demonstration.